Good morning. Today we will continue with high-angle X-ray diffraction. This is application of X-ray diffraction which we have learned during the last lecture. Actually, this method has many names. High-angle X-ray diffraction, high-angle backscattering, wide-angle X-ray diffraction, or out-of-plane Xrd are the common names used for the applications of X-ray diffraction. So we have three main aims or targets, let's say. One is determination of the crystal structure. So by using X-ray diffraction method, we can determine the crystal structure. We can determine the interplanar distance between the planes. We can determine whether the crystal is FCC or BCC. We can determine the lattice parameters. So you can get a lot of information about the crystal structure of the materials. In addition to that, you can determine the crystal directions, Miller indices. So whether your surface is 100 or 111 or 222, for example, okay, you can determine all these things by using high-angle X-ray diffraction. In addition to that, you can determine the crystal defects within your material. This is also very useful for some applications. So today I will discuss all these three important parameters in X-ray diffraction experiments. Let me start with the crystal structures. Actually, you know this information from the undergraduate courses, from associate physics courses, from your bachelor time. So cubic is the very common one. There is tetragonal and orthorhombic, hexagonal, trigonal, monoclinic, and triclinic. 7 crystal classes we have. 1, 2, 3, 4, 5, 6, 7. 7 crystal classes. In addition to that, we have different unit cells. Here we have blue ones. Blue ones are the primitive unit cells, and green ones are the body-centered unit cells. And here we have red ones, face-centered unit cells. And here we have purple or violet, let's say, site-centered unit cells. Okay, so 4 different types of unit cells and 7 crystal classes. And finally, we have 14 Bravais lattices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 Bravais lattices. Okay, so what is the crystal structure? In cubic crystal structure, all these lengths within the unit cell are equal to each other. A is equal to B, B is equal to C. Let me draw, or let me write here. Let's consider that this is A, this is B, and this is C. So all of them are equal to each other, and the angles are 90 degrees. So here we have one angle, here we have another angle, here we have another angle. So all angles within this unit cell are equal to 90 degrees. Okay, this is the cubic structure and very common in nature. So many materials have this cubic crystal structure. Tetragonal crystal structure is also very common. Okay, so what is the difference between cubic and tetragonal? Angles are same, A and B are same, but only C is different from A and B. So let's consider here we have A and B. They are equal to each other, but here we have a longer C, okay? A longer C in case of tetragonal. So the units, you can consider that cubic crystal structure is distorted a little bit. It is elongated, let's say. And this is orthorhombic. In orthorhombic crystals, A and B and C are completely different from each other, but the angles again are 90 degrees. In hexagonal crystals, we have A and B are equal to each other, and C is different from A and B. So I will go into detail with the hexagonal crystals later on. And here again, alpha and beta are 90 degrees, but there's a gamma here, which is 120 degrees. I will talk about this. There's a trigonal, monoclinic, and triclinic. So this hexagonal, this tetragonal, and also the cubic structures are very common in materials, okay? So at least you should remember the information related to this three crystal structure. So, do you have any question here related to the crystal structures?
No, clear.
Okay, then let me continue with the Miller indices. Here you see a cubic structure, many cubic structures, and here you see surfaces. These are showing the different Miller indices of cubic structures. Of course, depending on the crystal structure, the Miller surfaces also change, okay? So here we have this surface, for example, 001 surface in the cubic structure. So how to determine this surface name? Okay, this is the surface name, this surface. How to determine this one? Do you remember how to determine Miller indices?
Yes, I know it.
Okay, let me show you only one, and then let me continue. So here, for example, how to write this surface. So let's consider that this is unit cell, and x is 1, and y is also 1, and z is also 1. Okay, in order to determine this surface, you have to find where this surface cuts the x, where this surface cuts the y, where this surface cuts the z-axis. So from the figure, you can see that it cuts the x-axis at the infinite, and also same for the y, but it cuts the z-axis at 1. So this is 0, this is 0, this is 1. So this is all one surface. Here we have 100 surface, okay, or 100 surface. It only cuts the x-axis. And here we have 010 surface, 010 surface. So it only cuts the y-axis, okay, and parallel to the z and parallel to the x-axis. Here we have another surface. It cuts the x and z-axis at 1. And here we have another surface. It only cuts the x and y-axis at 1, and it is parallel to the z-axis. So here we have another different surface. So by applying this rule, you can find Miller indices of the surfaces. So with this one, I would like to finish the Miller indices with cubic structures. So here, what do you see? This surface cuts the x, y, and z-axis at 1. So we have 1, 1, 1 surface here. This is also very common in calculations, in problems, okay, and very usual surface in cubic structures. So now let me continue with the hexagonal structures. Hexagonal structures has this type of shape. Let me draw here. You can say that this is A, this is B, and this is C, okay? And what about 120 degrees? This is the 120 degrees, okay? All other angles are 90 degrees, okay? So what about the name of the surfaces in hexagonal structures? What we have learned that in cubic structures, we have 3 Miller indices. These are the H, K, L numbers, okay? For example, for 100 surface, H is 1 and K is 0, L is 0. But in case of hexagonal structures, what do you see? 4 Miller indices. You see, we have 4 numbers in the surface names. Okay, why we have 4 numbers? In hexagonal structures, we use this expression for the surfaces. And this is the L, okay, like this. So why we use this one? Otherwise, you can mix the cubic structure and hexagonal structure. For example, look at this one. So if you don't use this minus h plus k, you can write this surface like this, 001, right? But in cubic structures, this is also 001, okay? So you can mix them, so or you can confuse. For this reason, we use this number here, which is given with minus h plus k. So here you see different surfaces in hexagonal structures, and all of the surfaces here include an additional term here, which is given with h minus h plus k. Okay, also here. So in some books or in some papers or in some information in the internet, you can find this type of representation of this surface, for example. 1, 0, minus 1, 1. Okay, for example, for this one, you can see this type of expression, minus 2, 1. So sometimes we use like this, sometimes we use like this. You can put this minus on the top of this number here, okay? So they are showing the same surface. So these are the Miller indices for the crystal structures, and we can determine this Miller indices by using X-ray diffraction. For example, you have grown a zinc oxide material on top of silicon, let's say. This is silicon substrate, and then this is zinc oxide, okay? Zinc oxide has a hexagonal structure, and there are many surfaces of hexagonal structure. So what about the direction of the crystals, direction of the surfaces parallel to the surface of the film? So you can check whether zinc oxide structures are grown like this on the surface of the silicium, or you can check whether they are grown like this, okay? So this surface is something else, and this surface is something else. So zinc oxide can grow on this substrate with different surfaces. So by using X-ray diffraction, you can determine this one. This is very useful for determination of Miller indices in crystal structures, in thin film applications. So now let me remind you here interplanar distance. We have discussed this one during the last lecture. So what do you see here? DHKL. So we have different HKL numbers. For this reason, we should have different interplanar distance between the planes. Consider these two planes. Let me show you here. So let's consider that this is 001 surface, and you would like to get the distance between the planes of 001, okay? So this is the distance between two neighboring 001 surface, okay? So you would like to get the distance between these surfaces. So neighboring surface is here. Okay, you can consider like this, and you are checking for the interplanar distance for these surfaces. When you are applying this interplanar distance formula, you must be very careful. So depending on the surface, this interplanar distance will change. Okay, look at the cubic structure, for example. Here, if you put another surface here, so then here you have interplanar distance for 010 surfaces, okay? Here, interplanar distance for 001 surfaces. Actually, here interplanar distance is equal to A lattice parameter. Here interplanar distance is equal to A lattice parameter. But for complicated crystal structures, it is not as simple like this. And let me continue. For the cubic crystals, as we have discussed during the last lecture, the HKL number can also be written like this. Okay, this is the H square plus K square plus L square over A square. Okay. So you can imagine if you are looking for the HKL 100, okay, then what you will have, put 1 here, put 0 here, put 0 here, and you will have 1 over A square. Okay, then they will be equal to the lattice parameter in cubic structures. But in case of tetragonal structures, we have another parameter within this interplanar distance formula, which is given with C, because in tetragonal structures, the cubic structure is elongated, okay? So then we have C here. So you have to consider the C in your calculations. So depending on the growth conditions, depending on the pressure you applied on your sample, sometimes you can manipulate this C, okay? And this is also very useful information in real applications and for scientific purposes. And in hexagonal structures, again, we have A lattice parameter here and also C, okay? So this is the C, this one, this longer one, okay? And we have A, and these are the HKL numbers, and the formula is completely different from the cubic and tetragonal structures. So this is the interplanar distance, and this formula for the cubic, tetragonal, hexagonal, and for other crystal structures will be very useful when you are analyzing the X-ray diffraction data, which I will show you. Here we have an X-ray diffraction machine, X-ray diffractometer, and by using this picture, I would like to explain what is the measurement geometry for X-ray diffraction experiments. Actually, during the last lecture, at the end of my transparencies, I have explained what is the geometry of the X-ray diffraction experiments. Actually, we are carrying out theta 2 theta measurements or theta 2 theta experiments. Here, what do you see? Let's consider here you have your sample, okay? It can be square shape or it can be wafer, okay, with some certain diameter. And then here we have an X-ray source. You produce X-rays here. X-ray source is this one. Usually in laboratory X-ray diffractometers, we have X-ray tube, okay, sometimes rotating on a tube. But if you go to synchrotron light sources, of course, here you have very high intensity, which is coming from the beam line. So X-rays are coming with some certain angle to this surface, and they are diffracted and they go to the detector here. Let's consider scintillation counter, for example. And what do you see here? This X-ray source is located on a goniometer, okay? And this detector is also located on a goniometer. And here we have another axis for this goniometer. Here we have another axis, this goniometer. And here we have another axis for this goniometer. It can go in and out, okay? So you can change the position of the sample like this. So this is multi-axis goniometer. You can change many parameters, and all these angles, positions of the axis, let's say position of the X-ray source, position of the X-ray detector, position of the sample, and position of this stage on this Eulerian cradle. So you can change many parameters by using the computer programs, okay? So there are the special programs for X-ray diffraction experiments. So this computer, you can manipulate your experiment, you can start your experiment, and you can leave it, and it can continue itself. So this is the general X-ray diffractometer system. So what about the theta to theta scan configuration? Let me also draw this one. Consider that this is your sample, which is staying here, okay? And then you send X-rays with some incident theta angle. This is the X-ray source. And here we have detector. Okay, this is another theta for specular reflection. So as I have explained during the last lecture, there is another theta here, and then the angle between the incident X-ray and the X-ray goes to detector is given with 2 theta. So this theta is called as sample angle, and this 2 theta is called as detector angle, which I have explained during the last lecture. Okay, so this is theta to theta scan. So you manipulate theta, you change the theta, you change the incident angle, and simultaneously you have to change 2 theta detector angle, and you should always keep this relation. Okay, you should have always this relation for each incident angle, for each detector angle. This is the measurement geometry for the X-ray diffraction experiments, but there are also some X-ray diffractometers with this configuration. The material, the sample is staying like this, let's say parallel to the ground. And then here we have X-ray source. X-rays are coming with some certain theta angle, and they are reflected, diffracted to the detector with again same theta angle, and again you can get the detector angle 2 theta. So this is also diffraction geometry for the X-ray diffraction. And this type of experiments are also called as out of plane Xrd, okay? Because you send the X-rays from out of plane, okay? Here also. I will discuss what is out of plane Xrd, what is in plane Xrd in the forthcoming transparencies, but I'm just giving this short information here. Any question here?
No, thanks.
Okay. Then let me continue with the analysis of measurement results. So here we have a real result. Let me first of all draw the material. Here we have zinc oxide, and here we have aluminum oxide, okay, or sapphire. Another name is sapphire. So this zinc oxide has hexagonal structure, and this aluminum oxide has also hexagonal structure. So now I have carried out X-ray diffraction experiment. This is the theta. This is the theta, or 2 theta here. This is the detector. And here we have an X-ray source. Okay, so I have carried out this experiment. I have changed the theta and 2 theta together, and I have scanned the theta and 2 theta. So what do you see here? 2 theta started from 28 degrees and it goes to 40 degrees. Okay, I have increased 2 theta. So I have increased this angle, but simultaneously I have also increased incident angle. So I have, then finally I get this data. What do you see here? In the x-axis I record 2 theta angle, and on the y-axis I record the intensity read by the detector. Okay, during this movement of theta and 2 theta, we are recording the intensity which is coming to the active area of the detector surface. Okay, now how to determine that what is the lattice parameter, what is the interplanar distance of this surface, and what is the name of this peak, and what is the name of this peak. So what this data tells you, how to analyze it. In order to analyze this type of data, you must be very careful with two important things. One is Brecht's law, the other one is intensity. If you see such an X-ray diffraction data, you must be careful with two parameters. One is intensity, rate by detector. The other one is Brecht's law. So I can ask many questions here. And in order to answer these questions, these two information can help you a lot. Okay, so I'm asking one question. What is the name of peak? What are the Miller indices? What is the name of this peak? So this peak belongs to zinc oxide or aluminum oxide? Another question. This peak belongs to zinc oxide or aluminum oxide? Another question. So what is the lattice parameter of the zinc oxide? What is the lattice parameter of aluminum oxide? And what is the D interplanar distance of zinc oxide? What is the interplanar distance of aluminum oxide for the film grown at some special conditions? Okay, so in order to answer all these questions, these two important parameter information can help you a lot. Let me start with this one. Okay. First of all, you have to determine 2 theta and theta. So here I'm dealing with this peak, let's say. Actually, here we have superposition of these two peaks, and I am dealing with this one at the beginning. So what is the maximum point here? The position of the maximum point, let's say 34.2 degrees, let's say. Okay. This is the 2 theta. So 2 theta is 34.2 degrees. And then theta is half of it. Okay. 17.1 degrees. Okay. Then you have theta. Then you can convert this theta to the radians, and then you can calculate sinus theta. Okay. You can calculate this one. Then here you will have certain number. Put this one here. Then what we have here, usually you can take 1 here because this and lambda must be on the order of this number here on the right side. So usually we take n is equal to 1. So what is lambda? Here we have X-ray source, and if you are using copper K alpha, for example, wavelength is 1.54 angstrom. So it is fixed. You know this information. So just put this one here. Of course, sometimes this wavelength can be changed depending on the X-ray setup. But if you have a single setup in your laboratory, then it is fixed. So you know this lambda, you know this one. On the left side, all parameters are known. And on the right side, there's a sinus theta. And you have calculated this sinus theta here, okay, from the position of the peak. Then put the sinus theta here. So from this expression, you can get the HKL. Okay, you can calculate interplanar distance. So you have calculated interplanar distance. Then by using the formula for the interplanar distance here for the hexagonal structures, you can calculate A and you can calculate C. Okay, then you can find Miller indices. For example, this peak belongs to 001 surface of zinc oxide. Okay. And what is the meaning of that? This information tells you that once you have calculated Miller indices and once you know the surface of the zinc oxide, then you can tell that the zinc oxide grown on sapphire with this type of behavior. So this 001 surfaces are parallel to the surface of the thin film. Okay, so you can get this information. And what about this peak? So just calculate 2 theta here and just calculate theta and calculate sinus theta and put this information into the Brecht's law. Then you can calculate D, which is coming from this peak, okay? And I know from my old information, this belongs to aluminum oxide, and this is, I think, 1 minus to 0 surface, okay? So with Brecht's law, you can get a lot of information from this real X-ray diffraction measurements, but here I would like to tell you something else with the intensity. What I have told you that if you would like to analyze X-ray diffraction data, 2 parameters, 2 important information can help you. One is intensity, the other one is Brecht's law, okay? So what about intensity? What do you see here, intensity? So here we have a broader peak, okay? And here we have very sharp peak, more or less like delta function, okay? Very sharp peak. So usually such sharp peaks comes from single crystalline substrates, okay? And this type of broad peaks comes from the thin film grown on the substrate. This is the experience. There are many physical reasons for that, okay? Just shortly, I would like to discuss it here. Here, as a substrate, I have aluminum oxide, and here I have zinc oxide. The thickness of the zinc oxide is around 35 nanometer, and the thickness of the aluminum oxide, let's say around 0.5 millimeter, okay? Very thick compared to this film, zinc oxide. So if you see such sharp peak in the X-ray diffraction data, then you can easily, without any analysis, you can say that this may belong to the aluminum oxide, okay? So, but if you have very few numbers of layers, okay, if the sample is very complicated, if you have many layers, if it is consisting of multi-layers with different materials, then of course analysis will be complicated. But if you go step by step, you can also solve this type of structures and you can analyze this type of X-ray diffraction data. But here, if you see very sharp peak with very high intensity, okay, then you can easily say that it is coming from the substrate. So here you see some additional features. I also would like to discuss these additional features in this broader peak. In the broader peak, we have a main peak and we have satellite peaks around this main peak. So this is the main peak of this broader peak. And on the right side, I have one satellite peak. On the left side, I have one satellite peak. On the right side, I have another satellite. And on the left side, I have another satellite. So actually, here you can see some other satellite peaks here. So they also have here on the right side, but they are under the intensity of this main peak, okay? So what is the meaning of this satellite peaks on the left and right side of the main peak of this broader spectrum? These satellite peaks are showing that zinc oxide is grown very well and it has single crystalline structure, and these satellite peaks are called as low oscillations, okay? Shows the crystalline quality of the thin film here. So now let me continue with real experiments. Here we have a sapphire, aluminum oxide, and here we have a zinc oxide, okay, thin film. let's say 35 nanometer thickness, and then I send very energetic cobalt ions into this material with the energies of 40 kiloelectron-volt. So you bombard this sapphire and zinc oxide with very energetic cobalt ions. Okay, so since these cobalt ions are very energetic, can go into deep of zinc oxide and they can penetrate into the sapphire or not. It depends on the thickness of the zinc oxide layer and also depends on the properties of the zinc oxide. So I would like to learn that what happened to the zinc oxide after cobalt ion doping, cobalt ion implantation, cobalt ion doping, okay? So first of all, I have material without any cobalt ions. I have pure zinc oxide on sapphire, okay? Then I am carrying out experiments with this pure zinc oxide on sapphire, and I see such behavior in the X-ray diffraction data. This is the peak which is coming from the sapphire, and this is the peak which is coming from the zinc oxide, okay? Then I implant this material system, sample system with cobalt ions, energetic cobalt ions, and I increase the concentration of the cobalt ions. Here you see 0.75 times 10 to 17 ions per square centimeter. This is 1 times 10 to 17 ions per square centimeter, 1.25, 1.5. So I am increasing the number of cobalt ions enter into the material. So then I will investigate the effect of cobalt ions within this material. I have many questions. So cobalt ions can penetrate into the zinc oxide, and they can penetrate down to which thickness within the zinc oxide. And another question, do they penetrate into the sapphire substrate? Okay. Another question, do they destroy this crystalline structure of zinc oxide? Do they destroy the crystalline structure of the sapphire substrate? Okay, I have many questions. So without looking into the material by using very complicated methods, I can answer more or less all of these questions by carrying out X-ray diffraction experiment. Here I will show you. This is the pure zinc oxide, this red curve here, X-ray diffraction data taken from the pure zinc oxide on sapphire. And then these are 4 different data taken for different cobalt concentrations within this material. Okay, so let's have a look. If the cobalt concentration is 0.75, then I have this type of behavior. What do you see? This main peak, sapphire peak, is staying there. And then here I have very small shoulder on the left side of the sapphire, which is not present here. And what do you see? This zinc oxide peak shifts to the right side, and this nice oscillations is not present here, okay? In addition to that, I have an additional peak here. If I further increase the intensity, this feature here becomes more dominant. This is shoulder on the left side of the main sapphire peak. And what about this peak? So what about the intensity? So the maximum intensity of this peak is decreased, and I have another feature. If I further increase the cobalt concentration, this peak goes to the right side and the intensity decreases, okay? Intensity of zinc oxide peak decreases. This is one information from the data. And what about this one? Peak shifts to the right side. Zinc oxide peak shifts to the right. Okay, any other information here, and these oscillations are lost. Low oscillations. Oscillations are lost. Okay, here these are three information. There are three informations related to the zinc oxide 001 peak. Okay, so they are completely different from the main pure zinc oxide peak. So what about the sapphire? We have peak position which is same, which is fixed, but we have a shoulder on the left side of the aluminum oxide. Okay, so what about this one, this shoulder, and other information? And we have here an additional peak which is present in all cobalt implanted zinc oxide material. And what about this peak here? This is the fifth information from this data. At least 5 situations can be discussed here. So let me start from the first one. This one here. Intensity of zinc oxide peak decreases. Why intensity decreases? What is the meaning of intensity? Here we have a zinc oxide material, and here we have aluminum oxide, and here we have an X-ray source, here we have X-ray detector. So if the intensity is lower, it means that less photons come to the detector. So why less photons come to the detector? What is the reason for that? I have to answer this question. Okay, so what happened within the zinc oxide after cobalt ion doping? Then intensity is decreased. I can explain this one with the planes of the zinc oxide. If you have perfect atomic planes of zinc oxide, like mirror, okay, then if you send X-rays from the X-ray source, okay, from a perfect mirror, you can reflect them to the detector. Then you can have intensity at the detector. But if you destroy these atomic layers with ion bombarding, okay, you produces roughness on this planes of the zinc oxide, then some part of the intensity cannot go into the detector. So this lower intensity in the doped or ion implanted zinc oxide films shows that the crystal structure of the zinc oxide is destroyed due to the ion implantation. Okay, this was the first one. The second one, why peak shifts to the right? Why this zinc oxide peak shifts to the right? So this was the main peak position for the zinc oxide, this one. And now we have another peak position, goes to the right side. So look at the Bragg's formula. What I have told you that if you would like to analyze X-ray diffraction data, you have to consider two things, intensity and Bragg's formula. By using these two information, you can analyze everything within this data, more or less. So peak shifts to the right side. What about the angle here? If the peak shifts to the right side, then we have bigger this number. This left side is fixed, then D is decreased, okay? Interplanar distance is decreased after cobalt ion implantation. Why? Let's consider zinc oxide lattice, and we have atoms here, let's say zinc atoms within this hexagonal crystal structure, and you put cobalt ions into this lattice. let's consider here you put one cobalt atom and another cobalt atom. So what happens if you put two cobalt atoms into this zinc oxide lattice? So look at the periodic table. In the periodic table, we have cobalt here and we have zinc here. So zinc is a bigger atom than the cobalt, okay? So zinc atoms are bigger at the beginning. Now, here we have smaller cobalt atoms. Then this D interplanar distance will be decreased. There will be lattice shrinking, okay, due to the small cobalt atoms. And this is logic. This decreases interplanar distance. So I have also explained why this peak shifts to the right side. So another information, oscillations are lost. Here in the pure zinc oxide film, we have many oscillations, low oscillations. They show the crystalline quality of the material, but in case of cobalt implanted films, we have no oscillations, okay? So we have lost the oscillations. So what is the reason for this? The reason is that we destroyed the zinc oxide material and now we have much worse crystalline structure, okay, compared to the initial perfect crystalline structure of zinc oxide, pure zinc oxide. Okay, so we destroyed the crystalline structure of the zinc oxide. You can also get this information. Now let me discuss this one. We have a shoulder on the left side of the main aluminum oxide peak. Why we have this one? If you have such shoulder, it means that you have many peaks here. Okay, so you see superposition of these ones. So why we see peak on the left side of the aluminum oxide? So look at the aluminum here in the periodic table. Aluminum is located here. And here I have cobalt ions. I accelerate them and bombard this material with these cobalt ions. If they go into deep of the material and if they can enter into the sapphire, so what do you expect? Sapphire has also hexagonal structure, okay? And what about the aluminum atom within the sapphire? Aluminum is much smaller atom compared to the cobalt. If you put cobalt into the sapphire crystalline structure, then what will happen? Look at the sapphire. Sapphire is 1, 1, minus 2, 0. Okay, so different from the zinc oxide. So A plane sapphire. So let's consider here we have aluminum atoms. Okay, 6 aluminum atoms and aluminum atoms here and aluminum atoms here. So when you implant this material with cobalt atoms, if some portion of the cobalt atoms sits on the aluminum side in the hexagonal structure of the aluminum oxide, then what do you expect? Cobalt here has a bigger radius compared to the aluminum, okay? Then you may expect lattice expansion here, okay? So you may expect lattice expansion in all directions because now we have bigger atoms within the hexagonal crystal structure, okay? So D will be increased. Use the Bragg's formula to the sinus theta. If you increase the interplanar distance, then the sinus theta will be decreased. Then what about here? You have lower 2 theta. Lattice expansion and lattice shrinking during this processes is very small, but with X-ray diffraction you can see it. I mean, diffraction conditions are still preserved, okay? Here we have another peak which was absent here in the pure zinc oxide. Here we have an additional peak, so which is coming from the cobalt clusters. Okay, cobalt is also hexagonal, so you can also write this one in hexagonal form. So we have cobalt clusters. What is the meaning of cluster? So here we have discussed that some portion of the cobalt atoms sitting on the zinc oxide lattice or sapphire lattice. But what is the meaning of cluster? Clusters are the cobalt atoms. They form hexagonal cobalt structures, okay? And they are not located within the crystal structure of the sapphire. They are not located within the crystal structure of the zinc oxide. So they behave separately like a ghetto in the material, okay? So the cobalt atoms here in the aluminum oxide lattice are the substitutional cobalt atoms, and cobalt atoms results in a shift in the zinc oxide peak are the substitutional cobalt atoms in the zinc oxide lattice, but these cobalt atoms, cobalt clusters, are not located either in the zinc oxide crystal structure or sapphire structure, so they form hexagonal cobalt clusters and they stay, let's say, independent from the crystal structure of the zinc oxide and crystal structure of the sapphire. So what do you see here? This method is very useful and it gives lots of information, and the good thing is that you do not destroy your material during this analysis, okay? I have 1, 2, 3, 4, 5 data, and let's consider each of them takes half an hour or 1 hour, let's say. So within the 5 hours, you can get a lot of information about your material, what is happening within the material, okay? What happened after cobalt ion implantation? What happened to the zinc oxide? What happened to the sapphire? What happened to the cobalt ions, okay? You can get a lot of information by using X-ray diffraction method. Here, I would like to show you 2 more information. One is this one. Actually, this is intensity versus 2 theta graph, okay? But instead of 2 theta, I can plot it like this, QZ. This one, this pure zinc oxide, is measured in the synchrotron laboratory in Hamburg Synchrotron Laboratory, Hasselab, and the energy of the X-rays, 8 kilo-electron volt. So then the wavelength is this one, more or less. You can calculate by using the formula, this one. Energy is given with hc over lambda, okay? So by using this formula, put this energy here, you can calculate the lambda. And look at this one. These 4 data were taken in Dortmund at Delta Synchrotron Accelerator, okay? So here, there was a different X-ray energy and then different wavelength. If the energy is big, then the wavelength is smaller. So here we have smaller wavelength, okay? Then, so we have different wavelengths. In Delta, we have different wavelength. In Hasselab, we have different wavelength. So if you take this data from different X-ray sources, then what about comparison? You cannot compare them because if you change the lambda, then the peak position changes. So the peak position for the zinc oxide, theta, will be different for this lambda from the Hasselab and different for the lambda from the delta, okay? Depending on the lambda wavelength, you will get different theta value, but if you plot them, instead of theta, if you use QZ, 2 pi lambda sinus theta. So you change the lambda, but theta also changes, so you compensate it, okay? Then QZ is much better representation for the x-axis here to discuss and compare the X-ray diffraction data taken at different synchrotron light sources or taken with different wavelengths. For this reason here we use QZ. Here we have another data taken at Hazelab, okay? So energy is more or less around 8 kiloelectron volt and wavelength is around 1.54 angstrom. So here again we have pure titanium dioxide at the beginning, this rutile structure. This is the pure titanium dioxide, and this is the data from the pure titanium dioxide, more or less sharp peak you see. If you implant this titanium dioxide with energetic cobalt ions, what will happen depending on the cobalt concentration? So here we have X-ray diffraction data for different cobalt ion implantation doses. So what do you see that the position of the main titanium dioxide is fixed, and compared to the pure titanium dioxide we have an additional peak here, okay, and in addition to that we have shoulder here, and in addition to that we have cobalt signals on the right side which were absent here in the pure titanium dioxide. So analyzing this one, you can also get a lot of information what happened to your material after cobalt ion implantation, and you can discuss the position of the cobalt ions within this material. You can decide whether these cobalts are sitting in the titanium dioxide lattice or they form clusters, okay? So this is very useful method. With X-ray diffraction, you can get a lot of information about your material. Okay, then let me continue with the in-plane X-ray diffraction measurement geometry. At the beginning of my talk, I have told you that high-angle backscattering or high-angle X-ray diffraction or wide-angle X-ray diffraction method is also called as out-of-plane XRD. And up to now, I have discussed out-of-plane XRD. So what about in-plane XRD? And what you get by using in-plane XRD method, I will explain the differences between these two methods. So actually you are using the same experimental setup, but the measurement geometry is different, okay? So let's consider that you have iron, for example. Iron is BCC, body-centered cubic, okay? And let's consider that this is the cubic iron structure. So we have many unit cells within this iron, depending on the thickness, of course. Okay, so here I have one surface, here I have another surface, and here I have another surface, and here I have another surface. If you use out-of-plane XRD, X-rays will be diffracted from these surfaces, this parallel surfaces, okay, as here. So we have crystal lattice planes, okay, and then we send X-ray with some certain theta angle, and it is diffracted with some certain theta angle. This is out-of-plane XRD. But in case of in-plane XRD, again, let's consider cubic iron crystal, and let's consider you have many cubic cells. So look at this planes now. I send X-rays from this side, more or less perpendicular to the surface normal, okay? So in out-of-plane XRD, I am looking at these surfaces. In plane XRD, I am looking at these surfaces, okay? So here you see crystal planes in plane XRD, okay? So here you see crystal planes in out-of-plane XRD. So the measurement geometry is completely different, and you get different information. From out-of-plane XRD, you can get information from these crystal planes, and from in-plane XRD, you can get information from these crystal planes. Here, in case of out-of-plane XRD, you send X-rays with some certain incident angle to the sample surface, and they go to the detector. This is the X-ray source, and this is theta, this is theta, this is 2 theta. Here we have a film like this. Let's say thin film, okay, this one. Here we have the same thin film staying on the sample holder of the X-ray diffractometer, but now we send X-rays from this side. Now the detector is waiting here, and this is the X-ray source. You can consider this is theta, and detector angle is 2 theta. So I'm looking for the planes like this. Here I'm looking for the planes like this. This is the difference, okay, between in-plane Xrd and out-of-plane Xrd. So they give us different information about the same material. Here you can see a diffraction geometry for the in-plane Xrd experiments. Actually, here I have shown you a diffractometer for the out-of-plane X-ray diffraction experiments. So same diffractometer can be used for out-of-plane X-ray diffraction geometry, and also it can be used for in-plane X-ray diffraction geometry. Okay, here to give you more information about diffractometers, I would like to show you different diffractometer, regardless smart lab, which is also present in our laboratory. So here you see the material shining here. Okay, this is the material. And then this is the X-ray source, and this is the detector, and these are the optics and filters, okay, and also slits. And X-ray comes to the surface of the material with some certain in-plane angle, and then it goes to the detector waiting here. And there are also optics here in this path of the diffracted beam. So let's consider here you have a cubic unit cell, and you have this planes, okay? And if you rotate this one around itself, when you complete phi, 360 degrees, 180 degrees, and 90 degrees. So what do you see? You will see diffraction peaks related to each plane, okay, like this. 1, 2, 3, 4, okay, 4 planes related to the surfaces of this one. So if you have a hexagonal structure, you have 6 surfaces. If you have a C-plane, 1 surface, another surface, 3rd surface, and here 4th, 5th, and 6th surface. So if you rotate around itself by manipulating the phi, then you will get 1, 2, 3, 4, 5, 6 diffraction peaks from each surface of the hexagonal crystal structure if you have very nice hexagonal structure of the material. And with this one, I finish my lecture. Take care of yourself. Bye-bye.